Ladies and gentlemen, welcome. Today I would like to present you enzyme kinetics. Enzyme kinetics is quite important topic of enzymology, and the reason why we study enzyme kinetics is to model enzymatic reactions. For example, if you have some biotechnological process and you want to use enzyme to decompose some compound in some biotechnological plant, you have to calculate how much time you need for this, how long will it take, and for this purpose you have to somehow know how enzymes work at a different concentration of substrates or at different conditions. So this is what enzymology and enzyme kinetics studies. Another reason why we study enzyme kinetics is that enzymes are very often used as drug targets. So very often drugs acts as enzyme inhibitors, and if you want to somehow determine the effect of the drug on its target, on enzyme, you can use certain values such as Ki, inhibition constant, which I will introduce today. And for this purpose you have to know enzyme kinetics. So very important field where enzyme kinetics is used is drug discovery, when drug targets are enzymes. And another reason why we study enzyme kinetics is that enzyme kinetics makes it possible to learn something about the enzyme, about the structure of enzyme, and this is possible to do without like knowing the structure, the three-dimensional structure. Some enzymes or some proteins in general are difficult to crystallize or difficult to be studied by structural biology techniques, and is therefore useful if you can learn something like indirectly about the way how enzyme works. And I will start with some general kinetics, like general chemical kinetics. So if we have some chemical reaction where A goes to B, then it's possible to imagine that this chemical reaction, I have one example from, not from chemistry, but from daily life. So imagine that you take a bicycle and you go to some street in Prague and you lock the bicycle on some lamp in the street with a bicycle lock, and then you go away, and what happens? It's very likely that somebody will come and steal your bicycle. And if you do this with thousands of bicycles and you place them around the city, these bicycles are going to be stolen quite quickly. And at the beginning, the rate of this stealing of bicycles will be very fast. There will be disappearing, like if you express it in the number of bicycles being stolen per hour, it will be some high number. And through the time, as these bicycles will disappear and there will be less and less bicycles left to be stolen, this number will go down, and in some infinite time you end up with 0 bicycles available in the streets. So we can express it in terms of enzyme or in terms of chemical kinetics, like that the rate with which bicycles are being stolen, or bicycles here are A and B is a stolen bicycle. So we can express something like a concentration of bicycles. So I will use a square brackets. So if bicycle is A, then in a square brackets A is like the concentration of bicycle. And so this could be like a number of bicycles per square kilometer, for example. And how this changes with the time we can express as a derivative. So there will be derivative with respect to time, and this is the rate through which bicycles are disappearing from the streets, and this will be somehow proportional. So it will be negative values, so there will be minus because bicycles are disappearing. They are not their number is going down, not up, and this number will be proportional to the concentration of bicycles, and it will be multiplied by some constant. So if there is high concentration of bicycles, there is a very high probability that somebody will find some bicycle and steal it. And if there is very low probability or low concentration of bicycles, then there is a low probability that somebody would find it and steal it. And if there are no bicycles, there is nothing to steal. And this constant k somehow expresses how good are thieves in stealing bicycles. So that's how it works. And this is very similar in chemical kinetics. So instead of like a number of bicycles per square kilometer, you got concentration of the compound A, and the decomposition of the compound A is its rate is can be expressed by this equation. So it is a differential equation, and if you solve this differential equation, you get something like that. You get some concentration as a function of time, and there will be at the beginning some starting concentration, and there will be an exponential decay. And if this k is very low, then this decay will be very slow. If the value of k is very high, then this decay will be fast, but it will be always like exponential decay. Sorry, it shouldn't go under 0. That's just my first lesson with this graphical tablet. So this is how it works for such a simple reaction. If we have some reaction that A plus B gives whatever, C could be, then the rate of reaction, like derivative of concentration of A with respect to time, is again negative because concentration of A will go down, and now this will be some kinetic constant, some rate constant, and it will be multiplied by concentration of A and concentration of B. So again, if we can look to some analogy with stealing of bicycle. So in the previous example, we assumed that there is always the same number of thieves who steal bicycle. But let's imagine that if some thief steals a bicycle, instead of selling it, he can use it as a bicycle. He can ride it, and therefore the thieves who steal bicycle becomes like a cyclist. And so either there could be very high concentration of bicycles, and when there is a high concentration of bicycles and high concentration of thieves, they will disappear very quickly. But either you can run out of bicycles, or in some scenario when all these thieves would become a cyclist, you can run out of thieves. So either this A or this B will go down, and this would slow down reaction. So if you start here with this, again I will try to plot it. Sorry. So here is time, here is concentration, and if we start with some high concentration of A and low concentration of B, these lines would be parallel, and we end up in some situation like this. So there is no reaction occurring because we ran out of B, and if you just swap A and B, then there would be the same scenario that we run out of B. So this is how enzyme kinetic works. So if you have some a reaction like this with some stereochemical coefficients, and you want to know how its rate depends on this concentration, then you simply like multiply their concentration and multiply it by the rate constant K. So if it's like a reaction where two A's are being changed to B, then the rate would be, I will not write it again, it will be minus K and A square. Of course, it doesn't work like if you have some very complicated reaction like that. If you remember some reactions from inorganic chemistry where there was magnesium permanganate reacting with I don't know what, and there were some coefficients like 7 molecules of something reacts with 2 molecules of something. It's of course not like that you got some like something to the 7 multiplied by something to some B to the 2 or nothing like that, because always if you have some complicated chemical reaction, you can somehow dissect it into series of steps, and it's no more like a single reaction. No, it's not a single elementary reaction. So then the kinetics is a bit more complicated, and this is also the case of enzymology and or enzyme kinetics. And one more thing I would like to mention is like that if you have some series of reactions, so if you have like reactions that A goes to B, goes to C, goes to D, D, and so forth, and you somehow make such a series of a differential equation and you solve them, you would end up in something like that. You got, I will have A in black color, so there is a time and here is a concentration, and this concentration of A will go down. Then I will switch this. D will be a blue color, so it will go slowly up, or no, there will be some kind of lag here, and then it will go in the same rate. It's not like the same rate or negative rate as this one, but I did my best. And if you look at these intermediates, maybe it would be necessary to have more like intermediates, but if you have these intermediates, they will somehow go up and then they will be steady at the same concentration, or maybe here it will go down again. And if I try some green color, so it will go again like with a little bit of lag, and then it will go like this, and then it will also decay. But if you look if you look for this time period, the concentration of B and concentration of C is more or less constant. This is because B is synthesized in the same rate as it is being decomposed by this reaction, and the same for C. C is being synthesized in the same rate as it is being decomposed. And this we call steady state. It's not the same as equilibrium. Maybe equilibrium could be seen as a kind of special example of steady state, but steady state is much more broad term, and it means that the concentration of some compound is not changing. This is the same as equilibrium, but it's not changing over time. But unlike equilibrium, it's being like permanently synthesized from this A, and at the end you increase the concentration of D. So this is like a dynamic process in which like the A is being decomposed, D is being produced, but these intermediates, their concentration are more or less the same. And we will use steady state in enzyme kinetics, because in enzyme kinetics we can somehow decompose this reaction to different intermediates, and concentration of these intermediates are like constant during the enzymatic reaction, and this is therefore we can use this model of steady state to model enzyme kinetics. Another reason why we can use steady state is that if you have to keep in mind that enzymes are pretty big molecules. Like you got enzymes are proteins, they can have hundreds of amino acids, so they are typically, their molecular weight is something like tens of thousands of grams per mole. So if you have a concentration in some of enzyme in some milligram per liter, which is I think usual concentration of an enzyme, but it can be of course lower. Such a concentration, if you express it in a molar concentration, it's a really very small number, like nanomolar concentration or micromolar concentration, but micromolar concentration of an enzyme is pretty high, and therefore we have like if you compare concentrations of enzymes in enzymatic reaction and these substrates and products, they are concentration of enzyme is several orders of magnitude lower. So I will draw it on one of next slides, but it must be kept in mind that there is this very big difference in concentration. One thing I would like to also mention is, like I was talking about an equilibrium, so let's have a reaction from A going to B, but now it will be an equilibrium reaction. So we got some rate constant K1 and rate constant K minus 1 for the opposite reaction. And now if we want to somehow express the time evolution of this concentration of A, again by differential equation, so it will be like a derivative of concentration of A with respect to time, and this A is being converted to B, so its concentration will go down, and it will be by this constant by this reaction from left to right with a rate constant K1, and it will depend on concentration of A, because A is the reactant of this reaction. And at the same time A is being produced by the opposite reaction. So it's produced, so there will be plus, then there will be K minus 1, and there will be it will depend on the concentration of B, because B is the reactant of the opposite reaction. And in equilibrium, So I will draw it. It's better to draw it. So when we start the reaction, so we got concentration here and time, and we start from some concentration of A, and we'll use A, and it will go like this, and then I will have B in blue color, so at the beginning there is no B, and it will go like this. I try to write it or draw it in a way that they do not change anymore. I was not very successful, but you can imagine that they do not change. So here in this time period, we can assume that this concentration do not change, so the system is in equilibrium. So if it's in equilibrium, we can write that this is equal to 0, that the concentration of A is not changing. Also, we can write the same equation for B. It would be exactly the same, except these plus and minus would be swapped. So if you write that this do not change, we got something like K minus 1 B is equal to K plus 1 A, and we can redraw it, rewrite it like the B divided by concentration of A is equal to K1 divided by K minus 1, and this is exactly the equilibrium constant, capital K. So it's possible to measure or express equilibrium constant as a K1 divided by K minus 1, the rate constant in one direction divided by the rate constant in opposite direction. So this is about equilibrium, and let's start with enzymes. So the simplest model of enzyme kinetics is this one, that we have an enzyme which reacts with the substrate, and this is like an equilibrium reaction. So there will be K1 and K minus 1 as the opposite reaction, and it is not a real chemical reaction. It's just formation of a usually non-covalent complex. So let's assume that in general it's not in general non-covalent complex. It could be, there could be some covalent linkage, but in many cases it's just non-covalent interaction, so we will assume it as a non-covalent interaction, and there will be a complex of enzyme with substrate formed, and this complex enzyme and substrate will decompose with a K2 to enzyme and product. We will not assume at the moment this opposite reaction, because anyway, if we study enzyme, we do it by mixing solution of enzyme with solution of substrate and measuring the rate by which product is being formed. So at the beginning we do not have any product there, so we can neglect like some opposite reaction. So, and now how we can model these concentrations of these players of this equation. So I can start with the derivative of this complex enzyme substrate concentration with respect to time, because it's the most important, and this is being formed by this reaction. So there will be plus K1, and this reaction enzyme plus substrate will need two molecules to react with each other. So it's like like bicycles and thieves, so they have to somehow collide with each other, meet each other, so this this reaction, its rate will be proportional to some probability of collision, which is proportional to the product of their concentration. So, and this will lead to formation of this complex enzyme substrate. And this complex enzyme substrate can decompose by either this reaction or this reaction. So it will be decomposed, so there will be minus, then there will be K minus 1, and then there is just single reactant, so it's enzyme substrate complex. And it can be also decomposed by the reaction with a K2 rate constant, so there will be K2 and enzyme substrate complex. And you can easily write similar equations for enzyme, for substrate, or for product, but only these two are or only this one is now important for us. And why it is important? Because we can assume that this concentration of enzyme substrate complex in enzymatic reaction is in so-called steady state. So there is its concentration does not change in time, so its derivative is 0. And why it is in steady state? Because it's simply being formed by this reaction with a equilibrium with a rate constant K1 in the same rate as it's being decomposed by these two reactions. And especially in enzyme, if I mentioned that enzymes are quite big molecules, so you can draw some concentration profile as a function of time. And here I will draw, for example, first I will start with substrate, so substrate will somehow go slowly down. Then we got enzyme, here or here, and at the beginning there will be very tiny amount of enzyme, because like you got substrates in millimolar or micromolar concentrations, and you got enzymes in micromolar or nanomolar or even lower concentration, so it will be usually several orders of magnitude lower than the concentration of substrate, and it will go little bit down, and then there will be steady state. So I do my best to draw it like a little bit above of this line, and something similar will be with this enzyme substrate complex. So this enzyme substrate complex will be formed like in concentration a little bit below this initial concentration of enzyme. And this concentration here almost do not change, so it means that this system is in steady state. This enzyme substrate complex is being formed in the same rate as it is being decomposed, and therefore its derivative with respect to time is 0. So it is not its concentration does not change. Maybe I can add here product, so product will be formed like this. This is the product. So we have a steady state, so we can write here that this the reaction does not or the concentration of complex enzyme substrate do not change with the course of reaction. So I will write it again here, and I will have to switch the color, sorry. So we got a derivative of complex enzyme substrate with respect to time is equal to plus K1 concentration of enzyme, concentration of substrate minus, and I will maybe put it into a bracket, so it will be K minus 1 plus K2 and concentration of enzyme substrate complex, and this is equal to 0. So now what we can do with this, we can somehow simplify it, and for this we will use a concentration of enzyme. So here this concentration of enzyme in these square brackets is like a actual concentration of like free enzyme without a bound substrate. So if you make some if you have solution of enzyme, there is no substrate, and so the 100% of enzyme would be in like form without substrate, so the concentration of total concentration of enzyme would be equal to this concentration of enzyme in the square brackets of this free enzyme. And if you add substrate, then a part of this free enzyme can be converted to this complex enzyme substrate. It could be 1%, it could be 10%, it could be 99%, it could be any fraction from 0 to 1, and therefore we can write that like this total concentration of enzyme, I will use the symbol C, so or CE, like a total concentration of enzyme is equal to concentration of free enzyme plus concentration of enzyme substrate complex. So like this is always like constant during the reaction, and some depending on for example substrate concentration, the enzyme could be either prefer this form or this form, so these values can change, but in total this will be the amount of correspond this number will correspond to the amount of the enzyme that was added to the reaction mixture. And I can maybe write it in a way like that concentration of enzyme is equal to this CE minus concentration of enzyme substrate complex, and I will place this here. So I will get like K1 multiplied by CE minus concentration of enzyme substrate complex, and multiplied by concentration of substrate, and I can write this because there is a minus sign, so I can write it here, so it will be equal to K minus 1 plus K2 in brackets and multiplied by enzyme substrate complex. So now we can somehow multiply these terms of this bracket. So it will be K1 CE and concentration of substrate minus K1 concentration of enzyme substrate complex, and concentration of substrate is equal to K minus 1 plus K2 multiplied by enzyme substrate complex. And what I can do now is that I can just add this to both sides of the equation. So I will get K1 CE multiplied by concentration of substrate is equal to K minus 1 plus K2 concentration of enzyme substrate complex plus K1 concentration of enzyme substrate complex multiplied by concentration of substrate. And now I can scroll down a little bit because I'm lazy to write it again. So we will somehow express this enzyme substrate complex. So it will be that enzyme substrate, no, it's I will not be too, this is to erase, no, doesn't work, so I will not use this one and I will just rewrite it. CE concentration of substrate is equal to let's say K minus 1 plus K2 plus concentration of enzyme, concentration of substrate multiplied by concentration of enzyme substrate complex. And now we can like divide both sides of the equation by this bracket. So we get like K1 CE concentration of substrate divided by K minus 1 plus K2 plus concentration of substrate is equal to concentration of enzyme substrate complex. And now I will scroll a little bit down further. Sorry. So now I will maybe write here again the reaction. So it's enzyme plus substrate gives enzyme substrate complex, and this gives the product. And here it's K2, the rate constant. And what we are interested in is the rate of the reaction. So the rate at which the product is being formed. So the product is being formed by, so I will write it like the derivative of the concentration of product with respect to time is equal to K2. There is, sorry. Okay, I've realized how I can erase something. So it's plus because it's being formed. There is K2 and there will be concentration of enzyme substrate complex. And it's the rate of reaction. So the rate of reaction is plus K2 multiplied by this fraction here. So it's K1 CE concentration of substrate divided by K minus 1 plus K2 plus concentration of substrate. And I have here some error, something wrong. Yeah, I have here something wrong, so I forgot this is plus, but here should be K1 because it was here and I missed it. So it should be also here K1. Sorry for that. So here should be also K1 here. And now it's perfect. Sorry for that. So at the end we can divide both sides of this fraction by K1. So I will write this K2 to the top, so it will be K2 multiplied by CE and multiplied by concentration of substrate, and then I will divide this part of equation, this denominator, is it? Yeah, I think so. K minus 1 plus K2 divided by K1, and here we just end up with a concentration of substrate. So that's what we get, and now how it is useful for us. So the rate of reaction depends on, these are constants, and these are also some constant. So it's something like constant multiplied by concentration of substrate divided by constant plus concentration of substrate. So this top constant we call either V max or V lim, depending on, I think it's different from country to country, so I don't somehow force you to use one of them, but you can use V max or V lim. And this bottom constant is Km, or sometimes Km. With capital M, it's usually written like that. You write capital K and capital M as a lowercase, and if you are lazy to switch between uppercase and lowercase, so many people use like capital K and small m. So this is for like proper people, this is for lazy people. And what is it? How does it look like if you plot it? So you can plot it like this. So now at the y-axis we will have the rate of reaction, and on the horizontal axis there will be concentration of substrate, and this shape of the curve is hyperbolic, so it looks like this. And there is some this equation has some, or this curve has a limit here, which is this V max. So I didn't draw it properly, so here is like this asymptotically tends to this V max. And if you look at V max, the value of V max, and you calculate a half of V max, and then you go this way till you cross this line, and then you go down, you end up in Km. So Km is usually expressed, or it's expressed in concentration units. So it's the concentration of substrate at which the rate of equation is half of this V max. So if you have some enzyme with a low V max, it means that it will go like this, and it will be very slow at any concentration. If you have some high V max, it will be fast at any concentration. And if you have some enzyme which is with very high Km, it means that there will be very small slope, and it will slowly go towards its maximum rate. If you have a enzyme with very small Vmax, it will go very quickly close to this Vmax, and then it will be almost like horizontal. So at concentrations like if you there are some enzymes which work at like concentrations like this, in this range, and there are enzymes which work at concentration of this range. So if these enzymes work at this range, then the rate of reaction is more or less independent on the concentration of substrate. So this would be like in terms of chemical kinetics, it would be a zero order kinetics. If some enzymes work at very tiny concentration, or their Km is very high, then the rate of reaction is more or less linearly dependent on the concentration of substrate. So it's like first order kinetics if you express it in terms of the rate of reaction. Now let me do some small historical I will make a new slide. So let me make some small historical remark. So this model is called Michaelis and Menten model, and it was discovered by these people, and but it was discovered in slightly different way. What I have shown, this model was developed a little bit later, and it used this steady state model. But in this original model, what they assumed was that, I will write again these equations. So there is enzyme substrate complex being formed, and then it's decomposed to enzyme plus product. So what this Michaelis and Menten assumed was that this reaction here is in like equilibrium. So you got some equilibrium constant K, let's just call it K. If you look at equilibrium constant, is like equilibrium constant of this reaction would be like that concentration of AS divided by concentration of A multiplied by concentration of S. This is like equilibrium constant. Again, we can assume that concentration of enzyme is equal to concentration of enzyme plus concentration of enzyme substrate complex. You can put it, for example, here, and then you end up in something like that. Concentration of enzyme substrate complex is like some concentration of substrate, right? Total concentration of enzyme multiplied by concentration of substrate plus this K plus concentration of substrate, and then if you multiply it by K2, you got not here, but you got something like that. The rate of reaction is equal to this V max multiplied by concentration of substrate plus K plus S. So it's exactly the same reaction, same equation. The only exception is that here we got just this K instead of Km. So what their original model was like assuming that this first reaction is in equilibrium. So like this reaction is very fast. So always when you mix enzyme with substrate, it will be like this. It will form an equilibrium, and then there is a very slow reaction, which slowly like takes a little bit of this enzyme substrate complex, and this reaction is so slow and these reactions are so fast that it does not perturb the equilibrium. And this model I have shown you on like these previous slides is just a kind of like a generalization of this model, this original model developed by Michaelis and Menten. So the reason why I explain it here, or why I made this historical remark, is that when we can somehow say that this Km is close to some equilibrium constant of enzyme. I swapped it. It should be like equilibrium constant in opposite direction, and these two sides should be swapped. Sorry for that. So then you get something like that. So this Michaelis constant is very, very similar in numbers to the dissociation constant of enzyme substrate complex. Of course, there could be some enzymes in which these reactions are quite slow and these reactions are quite fast, and then this is not true anymore. But as a first estimation or first approximation, it's possible to say that the Michaelis constant somehow express this dissociation, or it's close to the dissociation constant of enzyme substrate complex. So if there is some enzyme with very low Km, it means that usually it has very low this dissociation constant of enzyme substrate complex, and it means that it's very strongly binding the substrate. And one more thing I wanted to add is that there are some enzymes which are fast because they have a very high Vmax, and so that's why they are fast. And there could be some enzymes which are fast because they have a very low Km. So either you can achieve high rate of enzymatic reaction in using high Vmax, or you can achieve a high rate of enzymatic reaction using low Km. And sometimes this is if you want to somehow like summarize, you don't want to use two different numbers, you want to use just one number. It's sometimes possible to use like Vmax divided by Km as a kind of like a number which expresses how good is enzyme in doing catalytic job. So some enzymes achieve some high number by having high Vmax. Some enzymes achieve a high number, high value of this fraction by having low value of Km. So some enzymes are very like processive. They can process many molecules of substrate at one moment, and some enzymes achieve it by having very low Km, so binding the substrate very strongly. And so sometimes you can find in some studies that, for example, people study some enzyme and then they introduce some mutation and they want to somehow express whether this mutation somehow change the activity. So of course it's better to show how does it change, how does Vmax change, and how does Km change. But if you want to have just one number for one mutant, you can use this fraction Vmax divided by Km. And one more thing I wanted to stress was that this Vmax, if you go several minutes before what I was talking about, is equal to K2 multiplied by concentration of enzyme. So this there are two like consequences of this. So first, like in normal enzymes, there of course are some exceptions. Like there is you should never say never in biological sciences, but in most enzymes, like the rate of reaction depends linearly on the concentration of enzymes. So if you add more enzymes, if you add twice as enzyme into reaction mixture, you should have a twice faster reaction. And then there is this K2, and sometimes it's instead of K2 you can see K cat. And why some people prefer to use this K cat instead of K2? In my opinion, the main reason is that in fact you can have some reaction like that. Enzyme plus substrate gives some enzyme substrate complex, and this can give something, and this can give something, and at the end there should be reaction giving a product. And this K-cat could be either this reaction, or it could be the sum of these, the rate constant of this reaction, or this reaction, or this reaction. I would just say that, like, in reality, the model, or the true model, which somehow, like, how the enzyme work, could be much more complicated than this simple, like, enzyme plus substrate gives enzyme substrate complex, and then it decomposes to product. Yeah, I forgot to put here an enzyme as well. But it could be much more complicated, and if you don't know which K is this K here, you can use some neutral name, and this is K-cut. And this K-cut is in if you look at values of K-cut, so I will write here again, like, there is a derivative of concentration of product with respect to time, so the rate of reaction is equal to K2 multiplied by concentration of enzyme substrate complex. So this is like I will just switch color. So now this is like in concentration of concentration units divided by time. So it's like a mole per liter per second, for example, and this is equal to something we don't know, and this is concentration. So if you divide, or if you somehow, like, decipher the unit for this K2, so it's in units like reciprocal time. So the K2 unit would be like a second per second, or second to minus first. So these K2 units are 1 divided by second, or second to minus first reciprocal second. So this K2 can be also, or this K-cat if you like, can be seen as either the number of moles of substrate which are being processed per second by 1 mole of enzyme, and because moles are the same number of particles, so it's also possible to express it as a number of or is this is the same value as the number of molecules which are being processed by 1 molecule of enzyme per time. So in this case per second, or it could be per minute, or whatever. So this is like the processivity of enzyme, and it can be expressed in this reciprocal seconds or reciprocal minutes, and this gives you the number of substrates, molecules being processed by 1 molecule of enzyme, single molecule of enzyme per second, per minute, or something like that. So I think it's all for, I will quickly check it, but I think it's all for the reaction which reactions which are not inhibited. And next time we can have a look at inhibition, because this will be something very important for drug design, and we will talk about different types of inhibitors and how we can measure their rate constants.